Welcome back to Mr. Hassan's Maths channel. I'm now answering a question which has been requested by one of my students at school, which is from one of the end of topic worksheets that I give them, and this is on S1, question number 4 from the worksheet on normal distribution, which is taken from the Solomon D collection from Statistics 1, and this is question number 6 from that worksheet. And it's a question here where we are dealing with normal distribution. It says a geologist is analyzing the size of quartz crystals in a sample of granite. She estimates that the longest diameter of 75% of the crystals is greater than 2 millimeters, but only 10% of the crystals have a longest diameter of more than 6 millimeters. The geologist believes that the distribution of the longest diameters of the quartz crystals can be modeled by a normal distribution. So you can say the diameter is such that it is normally distributed with a mean, which we have to find, which we will call mu, and a variance, which we have to find, which is called sigma squared. Okay, sigma stands for the standard deviation. The square of that is the variance. So one thing I'm going to make note of right away is that they're asking for the mean and variance, not standard deviation. So our answer for standard deviation that we're going to square it so we get the variance at the end. That's important for us to understand, not to lose one of the marks here. So now it says, first of all, it says, she estimates that the longest diameter of 75% of the crystals is greater than 2 millimeters. So you can say the probability, let's just get this, the probability that the diameter is greater than 2 millimeters is equal to 75%, or you can say 0.75 as a decimal. And also, the probability that the diameter is more than 6 millimeters, so it's more than 6 millimeters, it's 10%. Okay, and we know that they're normally distributed, so therefore we can use our normal distribution bell curve and our tables to get the answer that we need. So what I'm going to do now is I'm going to take a couple of copies of these bell curves, nice and neatly done, and I'm going to use those to put in, or to picture what's happening here. Now, a lot of students have a problem, and I just was going through one of the forums, and one of the students had a problem with this issue of how to know where, to put the line, whether it will be on the side which is where z is negative or positive. Okay, so for example, in the first case here, where do we put the line for where 2 millimeters is, and therefore where the z value we're going to find is? Now, when it says the probability that d is greater than 2 millimeters is 75%, 0.75. What we have to understand is the whole of the area is considered 100% or 1. Okay, 1, the whole thing is the area of the whole of this curve. And if it's such that greater than 2 millimeters is 0.75, 75%, that means 75% of the whole of this area is greater than 2 millimeters. Okay, so that means 2 millimeters must be somewhere on this side, such that the area to the right of it is greater than 2 millimeters, greater than 75%, so is equal to 75%. So most of the area is taken up to the right of 2 millimeters. So if that's 2 millimeters, this is your D values. Okay, this is the mean, which we don't know, we have to find. All right, but to the right of this value is 75% of all the data. Okay, so to the right of it, so this is 0.75 here. Okay, and here it says the probability that the diameter is greater than 6 millimeters is only 10%. That means greater than 6 millimeters is only 10% of the data, which is, of course, less than half of the data, right? So it must be somewhere over here. There's only 10% of the data to the right of it. So 10% is going to be a small amount, which is just over there. So this is going to be 6 millimeters. This is the mean that we have to find. This is the D values, right? And this is only 10%, which is 0.1. So what we got to do now is we got to find what the Z values are for this. Okay, the Z value that represents the 2 millimeters, and we're going to find the Z value that represents the 6 millimeters for D. If we find those two values, then we will be able to solve our problem. All right, how do we find these two values? Well, we go to our table of values of the normal distribution. All right. So what I'm going to do now is I'm going to go to the table of values, and first of all, I'm going to think about this first situation, and I'm going to actually grab the table over here. So first of all, I'm going to look at the table, the small table on the top of the formula sheet. Now this table, the first column is the probability or the area, and the Z value here, this is the area to the right of that Z value. In the top table, the small table here, it's the probabilities are on the first column and the Z values are on the second column, and the probabilities are the probabilities to the right of those Z values. Now the thing is, we don't have any negative Z value. This definitely is going to be a negative Z value. This is going to be a positive Z value. This doesn't have negative Z values. Right, it has positive Z values, but we've got to use the symmetry of this curve in order to work out what we're going to look for. Now, this is symmetrical. So there's going to be somewhere over here on this side, which is going to be exactly symmetrical to that. And the area to the right of this is the same as the area to the left of that. And this value, in terms of Z, is going to be exactly the same as that value, but just negative, because here this is 0 in our standardized value. The mean is 0. All right, the mean is 0 in the standardized form. So in this table represents when you have a mean of 0. So therefore, this value here and this value here will be the same numbers, but this will be negative, this will be positive. So if I find the probability that, and I can see that this small area here is 0.25. If I look for a probability of 0.25 over here, then I can use this table. If I don't find 0.25, which I don't, because I go 0.2, 0.3, 0.25 isn't here, then I can't use this table. I have to go to the bigger table. I have to go to the bigger table. Right, I'm going to first check on this side now, can I use this table for this? And then I'm going to come back and use the other table for this. So can we use this table for this? Well, this one's pretty easy because we have the area to the right of that value. So we're looking for an area of 0.1, okay? And we see there is an area of 0.1, which is right over there. This is the area 0.1. And the Z value there is 1.2816. So this is 1.2816. All right, so now we've got that value. And now I'm going to come back to this one and try to look at the other table to try and figure out what this Z value is. So now we've got to go to the other table. Now for the table underneath the little table, we have, I'll show you from here, we have basically the first column is the Z value and the second column is the area to the left of that Z value. Okay, so for example, we're looking for something over here. All right. Now, again, the Z values only start on the positive side. Okay, so if I'm looking for this area over here, okay, I'm looking for I'm looking for the probability, I'm looking for basically this is 0.75, that's what I'm looking for. Now, I can't find 0.25 here because they only start from 0 upwards. So what I can do is I can find the value here. So if we go back to this, what I can do is I can find the value on the other side of this, okay, such that this area is 0.75, such that this area is 0.75, and whatever Z value I get for this, I'm looking for the negative version of it. So I'll just, whatever Z value has 0.75 to the left of it, I'm going to take that Z value and write down its negative, just a negative of that value. So I'm looking for an area, I'm looking for the area which is called phi Z, all right, of 0.75. So I've got to look at the phi Z column and look for 0.75. All right, so I keep going down. Now I don't find 0.75, so I've got to look for the closest value to 0.75 that I can find on the table. So here you have 0.7486 and 0.7517. Well, this is closer to 0.75 than this. This is like 14 away, this is 17 away. So I'm going to choose 0.67. I'm going to choose 0.67 as my value of Z, but of course we're going to use the negative value because we're looking for this over there. So I'm going to use negative 0.67. So I know that the Z value here is negative 0.67. Okay, so now I found the Z value that represents 2 and the Z value that represents 6. This one I could write more accurately because I used the smaller table. Whenever you can use the smaller table, you use it. When you can't, you use the bigger table. So now I have these two values. I can now use my formula now to standardize all the scores so that they are in terms of the bell curve given in the formula book. Okay, what you do is you have Z equals a Z score. These scores are equal to the actual score, which are these 2 and the 6, minus the mean, which we don't have, but we have to find, over the standard deviation, which we have to find in order to find the variance. So I can form two equations, one from the first part of information. So I can say the probability that the diameter is greater than 2 millimeters equals 0.75 leads us to the equation where we have the z value is minus 0.67 equals x, which is 2, minus the mean over the standard deviation, which leads us to saying negative 0.67 equals 2, negative 0.67 times sigma times the standard deviation is equal to 2 minus mu. So that's one equation. And we can say the probability that the diameter is greater than 6 millimeters is equal to 0.1 leads us to the equation. We have the z value is 1.2816 equals 6 minus mu over the standard deviation. So we can say that 1.2816 times the standard deviation is equal to 6 minus mu, and that's equal. Okay, so now when we subtract these two equations, we will eliminate the mu, and we'll be left with sigma, the standard deviation. So if I subtract these two equations, I'll do it this way so it works out better. Equation 2 take away equation 1. So we have 1.2816 take away, and be careful here because it's negative 0.67. So it's going to be a plus there basically. So that gives us 1.9516. So 1.9516 sigma is equal to 6 minus 2 is 4. And what we wanted to do, eliminate this, minus mu, minus mu is minus mu plus mu, that disappears. So now we can find sigma. We can say therefore sigma is equal to, if you want to find what sigma, you've got to do 4 divided by 1.9516. So therefore sigma is equal to, so we have, so 4 divided by my answer, which gives you 2.0496. 2.0496. Now, the mark scheme for this says 2.05. However, that's the standard deviation. The actual question asks for the variance. This is from one of the Solomon papers, right? So it says variance in the question, and this is clearly the standard deviation, even in the working out that they show in the mark scheme thing. It stops at standard deviation, it says sigma equals. So really the answer for this would be the square. That's the proper answer according to what the question is asking. Okay, so you got to take the answer and square it, which gives you 4.20086. 4.20086. So to 3SF, that would be 4.20. That's the variance. Okay, this is the standard deviation. So the mark scheme says 2.0496, but the variance is actually 4.20. That's what the answer is according to what the question is asking. Okay, now we've got to find now the mean. So you take the mean, we can take it from here. If we rearrange this, add mu to both sides and add 0.67 sigma to both sides. So you end up with 2 plus 0.67 times sigma, which we now know is 2.0496. So mu will therefore be, so I'm going to go take the square root of this. Okay, this is our answer for the for this. I'll multiply this by 0.67 and I'll add 2 to it. And that gives us 3.3732. 3.3732 goes on. So therefore we can say our mean is equal to 3.37. So those are the actual answers. As I mentioned, you will notice it says this as the answer for the standard deviation, but they asked for the variance very clearly in the question. So I'm going to write the answer as it should be. That's the variance, and that is the mean for this question. All right, but standard deviation is 2.05 to 3SF. Then it says part B. It says the geologists also estimated that only 2% of the longest disc diameters were smaller than 1 millimeter. Calculate the corresponding percentage that would be predicted by a normal distribution with the parameters that you calculated in part A. So basically they're saying use the fact that the diameters are such that they are normally distributed with a mean of 2.05. I'll just write it to 3SF and a mean of 3.37, that's the mean, okay, the mean of 3.37 and a standard deviation of 2.05. I'll just call it 2.05 squared. That's going to be the variance, sorry. So 2.05 squared. Okay, so that's the mean and that's the variance. Okay, calculate the corresponding percentage that would be predicted by a normal distribution. So we've got to see what's going to happen when we use a normal distribution. Okay, so we got to use the normal distribution curve. So it says 2% of the longest diameters were smaller than 1 millimeter. So that means the probability that the diameter was less than 1 millimeter is equal to 0.02. Okay, that's what the geologist estimated. Okay, now let's see. That's the estimate. Okay, we got to see, all right, what according to ours is what the probability that the diameter is less than 1 millimeter is equal to. We got to find out what it is according to the normal curve. Okay, so this is what she estimated. This is what the normal curve would give. So we got to see less than 1 millimeter. Okay, so 1 millimeter is going to be here. We know the mu is 3.37. So for sure 1 millimeter is less than that. Okay, 1 millimeter is less than that. So 1 is going to be over here. These are our actual D values. Okay, so what we got to do now is we got to find out what the Z value is and then work out what this area is according to our standard deviation. Okay, according to our normal curve, sorry. So we got to find out what is the Z value, okay, for this. Okay, so we got to go to the D, we got to standardize this one. So we have Z equals X minus mu over the standard deviation. So we got to find the Z value for 1 millimeter. Okay, and that's going to be X, which is 1, minus mu, which is 3.37 over the standard deviation, which is 2.05. So we can say the Z for 1 millimeter is going to be given by this. You can say 1 minus 3.37 divided by 2.05, and that gives us negative 1.156. Negative 1.161, you can say. Right, that's the Z value. So we can write that to 2 decimal places because that's what we normally use. That's going to be minus 1.16. All right, so this Z is minus 1.16. That's the Z value here. And we've got to find what is the area to the left of this. Okay, now, so the probability that Z is less than negative 1.16. That's what we've got to find. Now, we can't find negative 1.16 on our table. What we can find is 1.16 on our table. And the probability that we're going to find is what's less than 1.16, which is going to be all of this. But what we know is that this area and this area are equivalent areas, exactly the same area because of the symmetry. So if I can say that 1 minus the probability that Z is less than 1.16 would be this area, because the probability that Z is less than 1.16 is all of this area, and 1 minus that is that area, which is what we're looking for. So if I find the probability that Z is less than 1.16 and do 1 minus that, it's going to give me what I'm looking for. So now I've got to go to the big table and look for Z as 1.16. So I go to the big table, I look for 1.16. 1.16 is right here. Okay, we can see here 1.16. It's 0.8770. That is the percentage to the left of that. So 1 minus that was going to be our answer. So 1.8770. 0.8770, sorry. So here we got 1 minus 0.8770. So we have 1 minus 0.8770, and that gives us 0.123. 0.123. So we can say that this tells us that according to the normal distribution, we can say the probability that the diameter is less than 1 millimeter is equal to 12.3%. 12.3%. Okay, so let's just get a bit neater. 12.3%. Okay, so hence comment on the suitability of the normal distribution as a model in this situation. Okay, so we can say it's not very suitable. Okay. Suitable as there is a large difference, as the difference between the estimates is big. Estimates is quite large. 12% and 2%. It's quite a large difference. So I would say it's not suitable. Okay, so that completes this question, which is question number 6 from the end of topic worksheet number 7. Question 4 from the end of topic worksheet number 7. Question 6 from the Solomon D paper for S1. Thank you for watching. Other questions from this particular Solomon D paper, when I get to answer them, this S1 paper will be found in the playlist that will appear at this region at the end of the video. Other questions from the end of topic worksheet number 7 on normal distribution will be found in the video appearing over here. Other questions which are from normal distribution in general that I've answered will be found in the video over here, and you can watch the video up here to show you how to use my channel in a very efficient way to find what you need. Thank you for watching, and see you soon.